In this video, we are going to finish up our discussion of section 2.6 part 2, Bernoulli differential equations, with one last example. So this example is not in the form that I would like it to be, so I'm going to move things around to try to make it look like a Bernoulli equation. So I got 1 over x, I like making it in that form. I'm going to add the square root of y over and change the power. That now looks like a Bernoulli differential equation, with n being 1/2. So we start off, we call this mu1 because if it's a linear dE in a moment, then we're going to have another mu. So we call it mu1, and this is always going to be y to the 1 minus n. All right, so I got y to the 1 minus 1/2, which means y is 1/2. All right, I can take that now, and I can take the derivative with respect to x of that equation, and we get 1/2 y to the negative 1/2 dy dx, because it's implicit differentiation. I don't know what y is. That's what we're trying to find. Now we multiply by, and it's always going to be the coefficient of your dy dx, so 1/2 y to the negative 1/2, right here. It'll always be right there. So we're going to multiply the dE by that. So we get 1/2 y to the negative 1/2 dy dx. Plus, and then we want to distribute this. Okay, so we get 1 over 2x times y to the 1/2 equals 1/2. All right, now we can replace with things that we have. I'm going to highlight some stuff here. We know that mu1 is equal to y to the 1/2. We also know, I'm going to change colors here, that mu1 dx is equal to that whole thing. So notice that this is here, and the other one is here. We're going to replace. Okay, so I replaced that first thing with d mu1 dx plus, I still have 1 over 2x times mu1 equals 1/2. Okay, now notice this is a first order linear. Can't spell, I guess. First order linear. So I'm going to use a mu2. First, you should consider, is it separable? It is not separable. You can play with it and see that. It doesn't work out that way. So mu2 is e to the, okay, we get 1 over 2x here, dx. So this is equal to e to the 1/2 ln of x, which is x to the 1/2. I don't have to have absolute value because it has to be positive for the square root anyway. So now I'm going to multiply my dE by that. So I get x to the 1/2 d mu1 dx plus 1 over 2x to the 1/2 times mu1 mu1 equals, and then 1/2 x to the 1/2. Be careful. I have a habit of forgetting to multiply by that on the side. So be careful not to do that. It's very frustrating. So by the theory of, and we should double check, this should work out to be the integrating factor times the independent variable. Should you check the product rule there? It does check out. The right-hand side I did not touch. Now, I integrate on both sides. Don't forget your dx's. Throw my 1/2 out here, x to the 1/2 dx. All right, so the left-hand side just comes out. That's why we do this whole method. It's nice and pretty. And then we get a 1/2. This is going to be times, okay, we get x to the 3/2 times 2/3 plus c, 1, just in case we have to change it. All right, those 2's do cancel out. I also am going to replace mu1. Mu1 was, trying to find it on my notes, mu1 was y to the 1/2 equals, okay, this is a 1/3 x to the 3/2 plus c1. We can go one step further. We can multiply by the x to the negative 1/2 to get rid of it on the left side. So we get 1/3. This is x, because I'm just going to minus 1/2 from that, so I get 2 over 2. plus c1 times x to the negative 1/2. That is a fantastic answer. It's a great place to stop. You could square both sides if you'd like to. It doesn't really do much for us simplifying wise, so we'll stop there. So those are Bernoulli equations. Most of the time, the problems that I see on test are that I have students that will do the Bernoulli side and then not have their first order linear stuff down. So make sure you have both things down for these.